Okay, so good morning. Welcome to our concrete class again. Really appreciate you taking the time to join us. Uh, Now we have talked about some of the design components in last lectures, and specifically, we are able to do analysis on single reinforced beam, analysis on double reinforced beam, and we also did design for reinforcement of single reinforced beam. That is, the section is given that you just need to design how much bars you need, how many bars you put into it, and what's the spacing, okay? And we also went over how to design a double reinforced beam. Again, that is, the section is given, you're responsible to find the design for the bars, size and locations and all that. Okay. And we also went through the details of our bar spacing details. For example, what is the minimum spacing needed for horizontal bars, and what is the minimum spacing needed for vertical directions of the bars. Covers, and we have two tables for you to use: 20.5.1.3 code. So we now are equipped with knowledge to do a concrete design now, isn't it? But we're still limited. Why? Because we are always under the circumstance that the section is given, geometry is given, right? So we are only responsible for finding reinforcement to make sure the design moment capacity proceed the applied moment, which is MU. So that is not a problem. That is not a problem. However, in the real world, most of the time we don't know the section, right? We start from scratch, okay? So today we're going to talk about how to design, okay? With unknown section, right? With no information on the section dimension, okay? So lecture 8, design of singularly reinforced, okay? Singularly reinforced. We're not going to do a doubly reinforced without any dimension information. We only do singularly reinforced beam, okay? With unknown section, okay? With unknown section. Okay, so that's lecture 8. And there are two objectives. First, okay, we want you to understand the definition of reinforcement ratio. Okay, so definition of reinforcement ratio, all right? And just right now, let's define it, okay? It's basically area of steel divided by the section area, okay? Assuming it's rectangular section, okay? So the second objective, of course, is learn how to design, right? Learn to design with unknown section. With unknown section. Okay, so these are our objectives. Okay, now before we start, right? So let's take a look at the design approach. What is the philosophy? What is the design philosophy? In other words, what is the design state? What is the design state? Okay, so I'm going to draw a section, and you probably know this very well. I have a rectangular section. Bigger. Nice rectangular section, no surprise, okay? And I have reinforcement at the bottom, okay? And a height, 8, but for now, let me just care about the depth D. And of course, I have a width of B. Okay? So I look at the strain diagram first. Right? So this is my vertical line, and I have a compressive strain at the top and tensile strain at the bottom. So my first question for today, let me see if it's available. First question today, Peter, Mr. Schenk, you there, Peter? Peter? Hello? Did I lose you again, Peter? Mr. Schenk? Can you hear me? Okay, I think you still have problem with your microphone, okay? Maybe let's take a look at it later, okay? Let's switch to a different victim then now. Wade, Mr. Compton, are you there?
Yes.
Okay, great, sir. So let's see, we have a compressive strain in concrete, right? So what is the concrete compressive strain and failure? What is the critical strain epsilon CU right here?
0.003.
Okay, thanks. So concrete compressive failure is 0.03, right? That's we all know, okay? Now, the issue is, what will be the tensile strain on the rebar? What will be the tensile strain rebar, right? When it yielded or when it failed, okay? And be careful now, we're talking about design. We're talking about design. So we will design the section to fail this way. We'll design the section to fail this way, okay? So that means I want my strain of steel, it has to be bigger than 0.005 to achieve so-called tension controlled limit state, to achieve this tension control limit state. And to be safe, I'm just gonna set epsilon T equal to 0.0075, okay? I'm just going to set that 0.0075. Okay, so this way I will ensure I have a section that still always yielded, All right, so if this is the strain distribution, I'm gonna look at the stress distribution, right? So on the top, the stress diagram looks like a Whitney stress block, right? Whitney stress block. And I have a 0.85 F prime C, a reduced compressive strength. And I have an effective compressive zone A equal to a beta 1 C. A equal to beta 1 C. And now I have a tensile stress in the steel, and I call it Fy, right? That's the tensile stress of the steel. Any questions? Okay. So in terms of total force, right? I have a compression from concrete that is 0.85 F prime C beta, well, right? In this case, BA. Okay. And I have a tension force T equal to ASFY. And mind you that right now we're only talking about singular reinforced case, okay? So this is what we call design state, meaning we design the concrete beam to fail this way. Now, we design it to fail in terms of compressive strain concrete reach 0.003, and simultaneously, the last layer of the bar reaches 0.0075. 0.0075, okay? So this is so-called design state. Now under this state, I know my compressive zone C is right here. So I can calculate my compressive zone C, okay? So C now equal to epsilon CU, that's 0.03 divided by 0.003 plus a 0.0075, okay? And multiply by the depth D. So you do a little bit of calculation, you realize that this is equal to 0.286 depth D. Okay? So that is the actual compressive zone size. So with that, I can compute my concrete compression in terms of 0.85 F prime C, right? And this is beta 1 C D, B, the width. So bring this number in, right? Bring this number in. And I get this number to be 0.24 beta 1 F prime C BD. Okay? So that is the design compressive forces from concrete. And let the tension equal to compression T equal to CC, that is ASFY, tension force, equal to 0.24 beta 1 F prime C BD. Right? So now with this, I can actually compute, right? So AS divided by BD, simply moving this term to the left-hand side and move Fy to the right-hand side. So equal to 0.24 beta 1 F prime C divided by Fy. Okay. And now, we defined this before called a reinforcement ratio. All right? And let me just put another subscript here called initial. means this is the target reinforcement ratio. Target reinforcement ratio. Okay. So this is a target or initial guess, right? This is initial guess reinforcement ratio. That means we will design our beam to have a reinforcement ratio of this value to achieve a 0.075 of strain in the concrete, sorry, in the tension and steel. 0.075 strain in the tension and steel. Okay. Now this equation looks a little bit odd. It's not satisfying, right? It's just point some number, very hard to remember. And I can see that this 0.24 is about 0.25. Make an approximation, right? That's about 1/4, a quarter, isn't it? So I can rewrite my initial reinforcement ratio into a simpler form. That is beta 1 F prime C divided by 4 Fy. So this is the target equation. This is the target equation. Okay. All right. So once we have this reinforcement ratio, we further introduce another concept. So we introduce another concept, right? Another concept is called reinforcement index. Reinforcement index. Okay. So let's define reinforcement index in terms of omega. Then omega equal to rho. Okay. Must be Fy divided by F prime C. Rho Fy divided by F prime C. Okay. And now with this reinforcement index, okay, let's take a look what the moment capacity is now. So recall nominal moment capacity Mn equal to ASFy, in this case, d minus Fa. Okay, where this is coming from, of course, this is the distance between the compression and tension, right? So that is d minus Fa. So put all these parameters in, I can see that, so A is equal to ASFy divided by 0.85 F prime C B, okay? And that is the effective compressive zone A. But let's play around, right? Let's make some manipulation. Let's multiply a depth D, divide by a depth D. Okay, see what happens, right? With that, I obtain the equation AS divided by BD, okay, multiplied by Fy divided by F prime C, and multiplied by D divided by 0.85. Okay, and I put all these numbers in. This is basically reinforcement ratio, rho, right? And this is the Fy F prime C, so Fy F prime C, but this whole thing is basically omega, right? So a reinforcement index right here. Okay, so essentially, I get a omega D divided by 0.85. Omega D divided by 0.85. And that is the effective depth. All right. So with this number here, with this parameter here, I'm gonna plug back in into the moment capacity. Okay. With that, then Mn becomes a different equation, right? Mn becomes ASFy. Okay. Bring this whole thing in D minus omega D, right? Divided by 2, 0.85. This is half A essentially. Okay, and then carry on the calculation. So Mn equal to ASFy and D bracket inside 1 minus 0.59 omega, okay, and then multiply by F prime C and F prime, oh, sorry. Okay, and that's what I have here. Okay. So this is not looking good still. This is not looking good still. Okay. So I'm gonna make a further manipulation. All right. Save you the hassle to go through it, and eventually we'll get a equation like this: omega F prime C 1 minus 0.59 omega and B D squared. All right. So now we obtain a nominal moment capacity in terms of reinforcement index. So we obtain a moment capacity in terms of reinforcement index. all right? And this just doesn't look good, okay? Doesn't look very coincide, clean, right? So I'm gonna introduce another parameter and I call it R, and this is so-called flexure resistance factor. Flexure resistance factor, okay? And with this factor, now call it R, defined as omega F prime C bracket 1 minus 0.59 omega, and red box it means you have to remember this. Okay? And with this parameter, things are easier. Things are easier. And now I got my moment capacity Mn essentially equal to R B D squared. How about that? Only 3 parameters. Right? So this is much easier. This is much easier. Okay? So why are we doing this? We're doing this because now, as you can see, the moment capacity is only a function of a reinforcement index, okay, and now section geometries. Okay, so this is section geometry. Okay, this is reinforcement index. So essentially, we decompose the moment capacity into 2 perspectives, right? 2 aspects. One is the reinforcement, the other is the geometry. The other is the geometry. And with this, we can carry on. Okay, so we say now, because we want phi Mn bigger than equal than or equal than mu, okay, so that means phi R BD squared, I'm just going to write it out, bigger or equal than mu. Okay, so that means we want BD squared to be bigger or equal than mu divided by phi R. Phi R, okay? So this equation is very friendly. This equation is very friendly. Why is that? I have left, it's called section geometry. Section geometry. The right-hand side, this is moment and reinforcement. Okay, so means on the right-hand side, we were given the moment and reinforcement. Left-hand side, I have my section geometry, right? So if I say let, right, the width B equal to a ratio multiplied the depth D, okay? And I want to constrain ourselves, say alpha is a number between 0.5 and 0.8. Okay, now after this is just design constraints, okay? Design constraints, meaning that limitations from the real scenario, right? Limitations from the real scenario. So I can convert my equation to be alpha d cube greater than or equal than mu divided by phi r. So d, which is the depth, right, has to be bigger or equal than mu divided by phi r alpha to the power of 1/3. And now, ladies and gentlemen, this is the geometry design equation. Geometry design equation. Now, recall for one layer, right? For one layer reinforcement, I have a relationship. Between the height of h and depth of d. Austin Horscam. Mr. Horscam, are you there?
Yes, sir.
So what is the relationship between the height and the depth now for one layer reinforcement? Give you a hint, it is d plus something. What's that number here? A quick help, tips. Is it 2.5?
Oh, yeah, 2.5.
2.5, right?
Yeah.
Good deal, thanks. So we have a concrete cover of 2.5 inch. All right, so that is what we have here. I'm gonna play a rule next time. We're gonna play the real Wheel of Fortune. You have options, the bypass or call a friend or something like that. Let's take a look at it next time, okay? So this is the depth, right? This is the design equation for depth. So now if I give you and apply the moment, okay, and give you a resistance factor design, you throw something in, which assume and another design parameter alpha, and estimated phi. Okay, for this case, always assume phi equal to 0.9 to start with. Always assume phi equal to 0.9 to start with. Why is that? Why can we allow phi equal to 0.9 here? Lucas, you there?
Yeah.
How are you doing, buddy?
Good. How are you?
Good. So why are we allowing phi equal to 0.9 here?
Because we're assuming we're setting the strain for tension as 0.0075 and it's greater than 0.04.
Right, that's correct. Okay, don't forget. Thank you very much. We have a tension control case. Tension control case. Okay, so that is the design process. But you don't have to remember all these equations. All you need to remember is the key equations, right? So let's label them. So first, we'll estimate. We'll give a design equation, right? So let's call it 8.1. Okay. We have this initial reinforcement ratio has to be guessed. And that is to ensure the strain still reaches 0.0075. Okay. With that, right, we introduce another reinforcement index. Okay. And this needs to be remembered. Okay. And with that, we introduced a resistance factor, R. And eventually introduced a moment equation, 8.4, and the end design equation, 0.5. Okay, so remember 8.1 to 8.5. Okay, remember all these 5 equations for design. Okay.
So the alpha can be 0.5 or 0.8?
Yes, alpha is an arbitrary number given by design constraints, but usually it's ranging between 0.5 and 0.8.
Okay, thank you.
Yeah, we'll take a look at an example, then you understand more, okay? But this is the general design procedure. As you can see, it's a little bit long, but not a whole lot of equation, right? As long as you remember this equation and use them, we should be fine. Okay, so now let's take a look. So example, right? Okay, so I have a simply supported beam. Okay, and I have a span length of 28 feet. Okay, and I have applied the moment, explained to you already, you don't have to recompute it, 153 kip foot by design, right? This is design moment. I'm gonna design for this. And the concrete strength is 4,000 PSI concrete, a whole lot, and grade 60. So meaning Fy equal to 60 KSI. So that is the design parameters. Okay, so first thing first, I can estimate height. My height. And by ACI code, H roughly equal to L over 12 to L over 18. So that is just a height estimation for deflection purpose. Okay, so with this, I obtain my height. Okay, I did the calculation already. Should be between 19 inch to 28 inch. Okay, this is just a range for the height, but it's not a specific number. Okay, all I have to do is make sure. We will need to make sure our design height, design H, fall in this range. Okay, fall in this range. What range? This one here. Okay, so whatever your design height come up with at the end has to be between these two numbers. So with this, let's start the process, right? So first, what is our initial reinforcement ratio, right? So what is that? So rho initial is nothing but beta 1 Fy divided by 4 F prime C. Got it the other way, sorry. F prime C divided by Fy, yeah, that makes sense. Okay, so bring number in 0.85 and 4 KSI. bottom here 4 and 60 KSI. Okay, and I got a number of 0.0142. Okay, this is my initial design. Proceed to get my omega reinforcement index, that is rho initial, which is going to be short here, ini, and Fy divided by F prime C. So I have 0.014 Fy, so 60 KSI, divided by 4 KSI equal to 0.21. Okay, and some of you are very smart, figure out already. If you take a look at this equation, right? Take a look at this equation, right? This essentially is beta 1 F prime C divided by 4 Fy multiplied by Fy divided by F prime C. So cancel just beta 1 divided by 4. Okay. So if you want to skip, you can skip, right? It's essentially you get the same number 0.85 divided by 4, it's approximately equal to 0.21. Same thing, same thing. Okay, anyway, so this is the reinforcement index, So now let's take the resistance factor R equal to omega F prime C, okay, 1 minus 0.59 omega, okay, so that is 0.21 F prime C 4 KSI, and 1 minus 5.9, okay, and omega is what? 0.21. Okay, and I have R equal to a 0.736 KSI. KSI. You notice something is different. You notice something is different, right? What is the difference between R and omega? Is that we have a unit. We have a unit. Okay, where that unit coming from? Now, omega is unitless. Rho is unitless, right? Both of these are unitless. They don't have any unit. They're just index ratio. But we'll bring all these numbers in here. I have F prime C in the resistance factor. So F prime R carries or inherited the unit of F prime C. So that's why I have a KSI. Okay. Now, approximately, R is at a level of 100 psi to 1,000 psi. Okay, it can be a little bit higher, but normally in that range. Normally in that range for our exam, okay? Normally in that range. All right, so with that, I'm just gonna assume some number. So I said alpha has to be between 0.5 and 0.8, okay? So set alpha equal to 0.7. You say why? Well, no reason, I just select the number, okay? And it's between the range. So I have freedom to choose, right? You can choose a slightly different number, that's fine. Right? So with this assumption, so D, which is the depth of the beam, has to be bigger or equal than mu divided by alpha phi r to the power of 1/3. So bring a number, top here 153 cubic feet, okay? And multiply by 12" per foot. All right, and divided by 0.7, which is alpha, and 0.9, which is phi, and 0.736 KSI, which is R. Okay, and don't forget the whole thing to the power of 1/3. So the depth now has to be bigger than equal than 15.8 inch. Okay, depth now has to be bigger than 15.8 inch. So this is very odd number. This is very odd number. Okay. So I'm going to use D equal to 16.5 inch, okay? 0.5 increment, 0.5 inch increment from the depth. Now H is the height, so roughly equal to D plus 2.5 inch, okay? That gives you a 19 inch, all right? 19 inch. But you know what, 19 inch is just not a good number for me. I want something, a whole number, right? So I want H equal to 20 inch. So easy for me to fabricate, easy for me to pour the concrete in, right? So now with this H equal to 20 inch, I'm gonna bring back in, so BD squared, remember BD squared, which is the equation right here, right here, okay? BD squared has to be bigger than mu divided by phi r. You say, wow, you just did that already, didn't you? You just derived depth, but remember, I changed it. I change it. So now, right? Okay. So now with the H equal to 20 inch, right? My real D, say, let's say actual equal to H minus 2.5 inch. My real D is now 17.5 inch. Okay, that's my real D now. Okay, so with this real D, I'm gonna bring into my equation to make sure BD squared bigger than or equal than mu divided by phi alpha r, no alpha anymore because I write it out. So outside this is 1/3. 1/3. So wait, I don't even have 1/3 anymore. Yes, BD squared bigger than that. Okay, so with this, I get my new width has to be bigger than or equal than 9.1 inch. Okay, plug in the D actual right here. Okay, plug in the D actual right here. Okay, so with this now, I would say select a width of 10 inches, just to be a wholesome number. Right? And with that, I have a section. I now have a section designed. So geometry right now, B equal to 10 inch. Okay, height equal to 20 inch. And that is my section. And I don't know what is my reinforcement area still. I don't know. But I know it's going to be 2.5 inch away from the bottom of the concrete. And I know that this section has to take care of mu equal to 153, I believe, cubic foot. Okay. So what to do? What to do is this. We need a rule quiz 5. Okay, is to find out what is the reinforcement area for this. Okay, what is the reinforcement area for this? Okay, all right. Today's going to be a short lecture since we're a little bit ahead, and also because I want you to guys maybe spend more time on homework number 4. Now you have it. So before I get into homework number 4, just got some quick questions. Do you guys have any questions on this? And we also have a quiz, right? Don't forget, we also have a quiz here. So we're going to find out the moment capacity of this section right here. And this, you have done this before. This is basically analysis, right? Analysis of singular reinforced beam. To add on, don't forget, this whole thing is based on concrete of 4 KSI, yield strength of 60 KSI. And you can use whatever bar you want, okay? And this would be a quiz 5, okay? All right, any other question on this, ladies and gentlemen? Are we good? Any questions? All right, so you might want to take some time to digest, but for the quiz, it should be straightforward. It's simply just analysis, okay? It's just analysis, all right? And let's take a look at the homework, all right? Let's take a look at homework. So let me open up. Any question so far? Quiet, okay, that means we're good. All right, okay, so let's take a look at homework, okay? Homework number 4 is very similar. Homework number 4 is very similar to the exam, all right? So I want to walk through with you to make sure you understand. Now, quick thing, right? It should be the same version as you've seen from the Canvas. This should be the same version as seen from Canvas, okay? Yeah.
It's posted on Canvas.
Hasn't posted yet?
No.
Okay, so I think I did, but let me post it again. But don't really worry about it because right now you can start working on it, okay? If you need more time, we can talk about tomorrow and maybe give you extension. But right now, let's stick on the schedule, okay? So take a look at this cantilever beam. All right, take a look at this cantilever beam. I have both the distributed load and the live load, okay? Both distributed load and live load give you a bending moment here at A, at section A here, okay? And you were given the square beam, 12 inch, 24 inch. You need to design the reinforcement in it, okay? Before we start anything else, right? Let me ask some quick questions here. Jack, Mr. Meadows, Jack?
Yep, I'm here.
Hey, morning, how are you, man?
Good.
Yeah, so which side should we put the reinforcement, top and bottom?
The top.
Right, great, so top, right? So now we just remember how to put the reinforcement top, Okay, now first question, if PLL live load with 5 kips, what is the factor moment critical section needed for design? So needless to say, the critical section should be here at A, okay? And you need to factor both the distributed and the live load, which is concentrated, right? To add up together, 1.2 dead, 1.6 live, okay? Now 1B, if live loads 5 kip, design the reinforcement of singular reinforced section using only number 8 bars, okay? We constrain the bars to be used only number 8. So you have to check out the beam width to see if you have adequate room to put the bars in. And then draw the cross section design with the rebar location, right? Don't forget the bar is going to be on the top. Okay. So number 2, we have a beam like this, distributed beam. All right. So consider reinforced concrete beam loading condition shown below. The beam self weight has been included, means you don't have to add on any self weight. The weight is here. Dead load is 10 kips per linear foot. Live load is 2 kips per linear foot. Okay. And the section detail is shown given the figure, all bars and number 9. Okay. That means first thing is, what is MU at section A? You need to draw a moment diagram. You need to draw a moment diagram. A quick question here. Bryce? Bryce? Hello, Bryce? Can you hear me, Bryce? Do we have... Hey, how are you, Bryce?
Good, how are you doing?
Good, good. So quick question here. So I have two support. Right? The triangle support on the left, the roller support on the right. So this triangle support right here, okay? Pay attention, the triangle support here. Is it a positive bending moment or a negative bending moment?
A negative.
Negative or positive?
Negative.
Negative, that's correct. Okay. So here at section A here, is it negative or positive?
Positive then.
Positive, exactly. So need to draw the section moment diagram in the sections first. Okay, moment diagram in the sections, right? So this is the first one. To be yes, question?
Since it doesn't explicitly say, can we assume that A is in the middle?
You mean yes, A is in the middle. Sorry, I should have mentioned. Let me make a correction on that, okay? So A is the middle span. Oops. I'll make a correction in the homeworks, okay? And then that's an MU at the section A. Second one, what is the effective depth of section at section A? So you have given the geometry, you were given the geometry, simply need to find the center of the group of bars and then find the effective depth that way. Okay. Now to see what is the stress reduction factor, right? To find stress reduction factor, we need to know the strain in the bottom rebar, right? In the bottom rebar, right? So we use DT or D. Tyler, Mr. Fink?
Yeah.
So do we use depth, effective depth D or DT to determine the stress reduction factor?
It should be DT.
DT, right? We'll always use DT. Okay. Now, some of you asked me a question, can we use D? Yes, you can, but be careful. When your D effective depth, right, lead you to a strain in the overall average of the bars that is smaller than 0.005, does not mean the bottom layer of steel have a strain that is lower than that. Okay, simply because the effective depth is higher than the DT. Okay, so be careful on that. All right. Last, just to check the design adequate for the apply moment. So this is more like analysis for doubly reinforced section. Analysis for doubly reinforced section. All right. Now, last problem. Design a rectangular reinforced concrete beam that resists the factored positive bending moment of this much, including all loads applied to the beam. All right. The width of the beam is set at 16 inches. You're given the width already. Okay. You're given the width already. Material strength is this and this. Concrete maximum aggregate size 0.75 inch. Pay attention, this means you need to design your rebars, design your rebar locations, right, spacings. And now you may assume number 3 stirrup will be provided for shear reinforcement. That means you use DS of number 3 stirrups for detail, okay? Perform all the required code checks design, basically the spacing, sketch the cross section, show the dimension and reinforcement. So now the width is given. The only thing that is not given is the depth D, right? So if I were to write it, you need to basically obtain D, right? D has to be bigger and equal than bracket inside mu. Can you guys see my annotation? Mu divided by phi. We just talked about this. At R, okay? And alpha, right? Bracket outside 1/3. And in this case, right? In this case, alpha equal to D or B, which is 16 inches, right? Divided by D. Okay. So this is the equation you use to determine D. All right. And after you get D, after you get a D, get a section, go back and do the analysis of singular reinforced section. Okay. Go back and do the analysis of singular reinforced section. Okay. All right. So this is the homework. Any questions on this? Any questions on this? Anything? Are we okay? Are we good on the homeworks? All right. So let me make a changes here. And I'm going to upload the homework to Canvas. Please start right away. Please start right away. It will take you some time. This homework will take you some time. And I will be here tomorrow, 2 to 3 o'clock for office hour. So bring all the questions you have on the homework. Okay? Bring all the questions you have on the homework. Now, some of the students are asking me about the first exam. The reality is we haven't set it yet. I will discuss with Dr. Sneed this week to determine the time and format the homework. Okay? If you still haven't gotten your code, ACI design code, reach out to me, all right? Please reach out to me if you still haven't gotten your ACI design code. Okay? All right, if nothing else, I'm gonna stop recording.